So welcome to MLF week 4. Last week we talked about how you go about actually building your neural network. This week we'll talk about how you go about training your neural network. Um, as a overview of what we'll cover, first we'll talk about a brief recap of week 3 and parts of week 2 and week 1. Then we'll talk about computational graphs, a heavy emphasis on gradient descent. And then finally, the concept of backprop and practical tips for when you actually train your model. Okay. Okay. So over the, I think, past 3 weeks, you guys have learned more or less two types of machine learning problems. First is like your regression problem. Week 1, you learned about linear regression. We're predicting some continuous value or, some continuous output. And then in week 2 and 3, we were talking about mostly about classification. So like your numbers or like predicting whether or not uh, it's within the circle or outside the circle. So then, what models can help us solve these problems in week 1 and 2? We talked about linear regression and logistic regression. And in week 3, we talked about neural networks. Again, the ultimate thesis of week 3 was neural networks are just a composition of functions, and it's a composition of an activation function with a weighted sum, and an activation function and a weighted sum, and an activation function and a weighted sum, and an activation function. Am I beating a dead horse here? Okay, look, it's an activation function and a weighted sum. Okay. And each node is a function, right? With an activation function and a weighted sum. And each neural network is a composition of functions with an activation function and a weighted sum. Okay. Now, I guess the question, I guess this is generally for all types of different machine learning models, is there a way to quantify how well our model performs? And the metrics that we learned are the mean squared error, which quantifies the distance between our predictions and targets, and then cross entropy loss, which quantifies the number of misclassifications the model predicts, right? And it's important to define these like metrics or these functions that define how well the model performs, because based on this, can we get a good model? Like, can we use our loss function to get the best model? Okay. And so today is all about, I don't think there's been a strong emphasis on this, but today is all about how do you build your best model? How do you get your best model? And what does the best model mean, right? So in our case, it'd be finding the weights or parameters that minimize the loss function the most. And as a brief recap, in week 1, we talked about gradients, which determine the direction that the weights should move to minimize the loss. And then we also talked about this alpha learning rate, which determines the magnitude by which you should move. Okay. Does anyone have questions so far? Is this okay? Cool. And then just as a small thing, learning rates, if it's too big, you won't converge to your minimum loss. And if it's too small, then it takes too much time to converge to that loss. Okay. If you get this concept, I think we're good for the rest. All right. So just to motivate before we get to neural networks, just to motivate how neural networks, or how do you train like a neural network? We'll talk about computational graphs. Now, with a computational graph, it's like a way of visualizing your symbolic expressions, where each edge represents an input to a function, and each node is an operation or a function. So, like if you look at this, what expression or what equation are we representing here in terms of A and B? I mean for E, yeah.
E is A plus B times C.
Yeah. A is, oh, sorry. A is A plus B times B plus 1, okay? And then we have these intermediate variables of C and D, okay?
Sorry, the set is cut.
Oh, it's cut?
There's a way. It's the aspect ratio. Go to set. More. Is it more?
Setting, recording.
Share screen.
This is full screen now.
Fit to content. I think fit to content.
This one.
You try. You could try.
Oh, no.
Oh,
All right, cool.
that is good. Yeah.
Okay, right. Computational graphs. So I guess the motivating question here is, how does changing A or B affect E? Okay, that's a motivating question. And today is all about how does changing one input affect the output. Okay, that's the basic theme or way of thinking for today. So just to put down some numbers initially, we'll set A and B equal to A equal to 2 and B equal to 1. I guess as a naive approach, how would you want to make E change with the inputs? We can start off there. We want to quantify how E changes as we change the input, as we change, the value of A and change the value of B. How would we want to figure out what that is? Yeah. Okay. And then we have expression. I guess like specifically the values. I'm talking more about that. Yeah. Yeah, I guess that would be okay. What I'm trying to say is like if you change that is the right solution. You just compute the derivative. What I'm trying to say is like never mind. If you guys can understand derivatives, then we don't have to talk about this. But what I want to motivate here is what you could do is you can change A to like 2.1, 2.2, and see how E changes. Or you can change B to like 1.1, 1.2, and see how B changes. Okay? Or how E changes. And so if we want to quantify how how E is affected by B's inputs, the general thought process is we want to figure out how does C and D affect E. And then from there, we want to figure out how does A and B affect C and D. Okay? We go layer by layer. We first look at the previous layer. Once we can somehow quantify this change, we go back one more layer. And then we try to combine them together. Okay? So I guess for now, let's say I changed the value of C equals to 4 while keeping D the same. How much does E change by? What value is D? And the same question goes. These are all questions for you guys. What do we think? What do we think? What do we think? Yeah. Yeah. For D. Or for E, yeah. And how about the bottom one? How about for C? That one. Okay. Okay, and then we can quantify this change using, like you said, derivatives. So then in this case, what would be the derivative for E? Or the derivative of E with respect to D? All right, someone else. Yeah.
0.
Uh, I guess you wouldn't look at this E equals 6 value. You would look at, yeah.
All C's.
Yeah, C. Yeah, it's just if you go back to your derivative, rules, the product of two variables, it would be, since C has a power of one, it would become 0, and then you get 1, and then you get C. Okay. And then the next question is, let's say, I guess the key point here is, let's say we change B now, okay? Let's say we change B from uh like B equals to 2. How much does C change by, and how much does D change by in that case? Yeah. Increase of 1, increase of 1. Yeah, yeah, yeah. That's correct. So in this case, if we take the derivative of C with respect to B, and D with respect to B, there would both be 1. Okay. Now, and unfortunately, we can't just like use our normal chain rule, because there are multiple paths, that if we change B, there are multiple paths that change can affect, and cumulatively that will affect the change of D. I mean, change of E, right? So then if we change B again by 2, how much would E change by? How much would E change by? Yeah, increases by 2. Is that right? Wait, let me give 1 second. Yeah, yeah, okay. It increases by 6. Sorry. Yes, 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 that's correct. That's correct. Increases by 6. And then I guess what the intuition here is, if there are multiple paths that one input can affect for an output, you would want to sum up all the paths that one input can affect. Okay. That's basically my main point here. And you would figure out that it's actually just C plus D once you plug in all the numbers. Okay. So key point, if there are multiple paths, sum up every single path by that change in the input. Okay. I'm pretty sure we didn't cover how you go about training logistic regression. So I guess we'll motivate it here right now. The problem with logistic regression, or the problems that logistic regression tries to solve, is like, you want to find the optimal decision boundary, right? So in this case, the optimal decision boundary would just be, some horizontal line here that separates class 0 and class 1. Okay. And if we want to define our logistic regression, or like single perceptron, if we want to build it in the code, we would use this initialization function that you should have looked at last week. And I guess as a brief exercise, again, what would Z be here and what would Y be? This is all just, yeah.
C is WX plus P.
Yeah.
Y is an activation function times.
Yeah. But yes, correct. So Z would be a weighted sum of omega 1 x1 plus omega 2 x2 plus B, and then Y would be the sigmoid function around your pre-activation Z. Okay. Now, our objective here is to find the best weights to define our decision boundary. And again, our definition here is to find the weights and biases associated with the minimal loss. Okay. So we have some initial state, our initial guess about our weights. This is our decision boundary. Obviously, it looks terrible because this doesn't separate class 0 from class 1. And we want to somehow change it so that it looks like this. Okay. So for forward pass, this is when you write code, this is what you're going to do basically when you do the define forward function. It's split up into 3 steps. You have initialization, predicting your targets, and then calculating your loss. Okay. So for step one, you want to, give your weights some value, right? So that you can determine how good is your current weights and how good is your current bias. So let's just give it some values. I picked the worst possible prediction in the beginning of -10, -10, 1. And then after you initialize your weights, you want to see what or how much loss that is. And that would be, again, with your forward function where you're taking your training data and inputting it into your model. Okay. So in our instance, I'm just going to take this single red dot, which has like an x1 value of 0.4 and x2 value of 0.8. Okay. So again, we said that y is the sigmoid of our weighted sum. If we compute this out, if we plug in all these values, we find that y is approximately 0.00167, and then based on what we learned before, our prediction would be 0, even though the class label is 1, right? And then for our last step during the forward pass, we would define some metric, our loss function. And in code, it will look like writing this criterion equals to cross entropy loss. And we find that the cross entropy loss, when you calculate it, it's around 11. Okay. And then for training, after you calculate your loss, you want to go backwards to update your weights, right? So this was what I would call backward pass. And in doing so, you want to calculate the gradient with respect to your weights, your weights and biases, your parameters, okay? And again, in a similar sense, you're going to look back at the most recent previous layer, compute the gradients, and then you'll repeat this cycle until you get your loss or the gradients of loss with respect to the weights. Okay. So again, we just look at this part of the graph. If we want to quantify how much L changes when Y changes, we would write the partial of L with respect to Y. If we want to see how Y changes when Z changes, yeah. T is our target. So in the cross entropy loss function or equation, you have that target value. Yeah. So if we want to quantify how much Y changes when Z changes, we would take the partial of Y with respect to Z. And if we want to quantify how much Z changes when W changes, we would take the partial of Z with respect to W1, Z with respect to W2, and Z with respect to the bias. Okay. And then what we would want to do is split, we've kind of split our original graph up so that we have this, each of these partial derivatives. And then from there, we can multiply them together to get our loss with respect to the weights. Again, we're trying to figure out how does changing our weights affect our loss, okay? This is just how does changing our weights affect our loss, okay? We're trying to figure out in which direction should we move our weights, update our weights so that we can minimize our loss. Okay, everything I just showed you is that. Okay. I guess as a brief exercise, I would like you guys to compute the partials of Z. I'll give you guys maybe 2 minutes, 2 minutes for this, for these gradients, for these derivatives. I've given you the partial of loss with respect to Y and then the partial of Y with respect to Z. And I just want you guys to figure out what these values are. You don't have to compute the final gradient. All I want is these derivatives. question? If you have an answer. If you have an answer, you can just raise your hand and we can just, yeah. Yeah, 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 okay. So if you take the derivative, again, it's the, you know, you can go back and look at the power rule, but if you take the derivative, you'll find that this first derivative is x1 because there's one weight. The second derivative is x2, and then the last derivative is 1. And then we want to combine all this together to then calculate our loss with respect to our weights. And then we can simplify it. Again, all on your free time, you can look at this. But when we simplify it, we get this value. Okay. So we've made a equation for how we should update our loss. Now we can use gradient descent where, for our current guess, we subtract it by our gradient times some learning rate. And I'll show you a sample plot just to give some more intuition. So we look at this. This is our optimal decision boundary. Okay. This is our initial guess. Okay. And if we graph the loss with respect to our weights, we'll find that, I guess, what is this red line? What do you think this red line would be? Yeah. Yeah, yeah, yeah. So this is our loss function with, all potential, what our potential weights can be. And at this point, this is where we initially are. Okay. This is like, we think our weights are -10, and 1, right? And obviously, if we look at it, that's not the minimum. So as we continue doing gradient descent, it's traveling down this path until it reaches 0. Okay. Okay. That's all I want to show for this. And then for this update rule in terms of code, you'll be writing optimizer.step. That's how you do the update. So for each step, you're moving down that loss function or loss landscape. Now, I guess part of today, we'll briefly talk about optimization algorithms. So for optimization algorithms, there are a bunch. All of them more or less do the same thing. Okay, they calculate gradient, and then they move the weights. Okay, there's just fancier math of how you go about calculating your gradient, or how you go about actually updating your weight. Okay, and then for stochastic gradient descent, instead of updating based on, um, summing all of your training examples, you only pick one example to then update your weights. And I wanted to do a live demo and get volunteers, but it's very narrow here. So actually, can I get 4 volunteers or 5 volunteers? Come up. Come up. Yeah, yeah, yeah. Come up. 5 people, 5 people. Okay. 2 more. Okay. I need one more person. All right. Yeah, okay. Let's see. I guess I'll be part of it. All right. So you stay there. Everyone else come with me. Come. Okay. You will be my batch gradient descent. Okay. We'll calculate. You are the most optimal path for our loss landscape. What's the most optimal path to that guy? He's our minimum.
In the straight line.
In a straight line, right? You will be a variation, and you'll be a variation. So when we sum up, all our loss, what we're doing is we're finding the most optimal path. It's just straight line, right? But when we do stochastic gradient descent, you're going that way. you're going, I guess every time you move that way and then you move that way. Okay. If you move, I move first. Okay, and you move, you're like a pair. You move next. And then you move next. And then you move next. All right, you guys should be cool. I guess when you guys move with each other. Okay, so all I'm trying to say is, what I'm trying to say is, this might not be the most optimal path, but every time they take 4 or 5 steps, this guy, our most optimal path only takes 1 step. Okay. Here. All right, you guys keep moving. Every time they take 2 steps, you walk. But you guys aren't supposed to walk in a straight line. You guys are supposed to zigzag a little bit, zigzag. Okay, maybe this physical demo wasn't the best example. Thank you for coming up. Thank you for coming. You guys can give them a round of applause. Give them a round of applause. Well, basically, what I'm trying to say is, when you take stochastic gradient descent, you don't have the most optimal path, but you're moving in the direction towards that minimum loss. Okay, versus your actual optimal path, which is summing up over the entire all your training examples. Okay, that's what I'm trying to say. And I guess I'll show another graph of okay. So in this instance, this 3D plot would be our loss landscape. You'll see all these trajectories going towards our minimum. You'll see like our stochastic gradient descent, stochastic gradient descent. These are all different optimization algorithms. And at the end, you'll see Adam, right? And Adam W, okay? Obviously, we see that Adam W does the best, and everything else does like kind of decently at going to the minimum. So even though there's no like perfect minimum, okay, there's no like quadratic function more or less, right? Our optimization algorithm can always update our weights so that it moves to our minimum. I'll show you other more exotic functions like this. Okay, even though this looks like a whack function, there is a minimum here, and our weights are still moving towards that minimum. Okay, that's it. That's all optimization algorithms are. Okay. All right, let's talk about, and in code, you would define what your optimization algorithm would be. So here, since we want to use Atom, we would write torch.optim.atom and whatnot, okay? Now backprop, okay. I feel like backprop makes sense if you get the sum over all paths and you get that how you compute gradients. That's basically backprop. I think the main issue with training your neural networks is like you have to compute a lot of gradients, okay? Because you have a bunch of weights to update. So the question is, how do you do this efficiently? Okay, so take the same example as last time, our spherical data set. We have this neural network. Again, as a brief recap, okay, each neural network can be vectorized in this format, where, again, we have an activation function and a weighted sum. And our objective is to find the best weights, okay? All our weights are these blue lines. You can imagine, like, instead of having 3, we have 4. Or instead of having 3, we have 100. The amount of weights that we need to update like explodes really, really fast. So finding a way to efficiently update it is crucial. Okay, again, we want to find the best weights to minimize our loss. Okay, again, step 1, we're doing forward pass here. Step 1, we're initializing our weights because we want to figure out, we want a number to, update basically. Let's see, what's your favorite number? 8. Okay, sure. I put 5, but we can put any number we really want. Okay, 8, 5 doesn't really matter. Okay. Later we'll talk about, certain techniques you should use when you initialize, but for now, let's just say we all put all 5s, whatever. We take a training data example, okay? And then we compute again, we're fitting all that training example, we're putting in through our equation, and we're computing our targets, okay? Again, it's a function. So we can, when we put in our training example here, it would calculate this weighted sum, then activation function. Then it goes to here, weighted sum activation function. Then it goes to here, weighted sum activation function. And then we get our prediction. Okay. And then we would define our loss and calculate the loss. Okay. So this is our forward pass. At this step, we would now want to kind of calculate our backward pass, which is calculating, again, how the loss changes as we change our weights, okay? And I've only added these two as an illustrative example, but there are many, many more weights that you'll have to update, and we'll talk about how you would go about doing that later. Okay, again, we're trying to find how our loss changes as we change our weights. Okay. So we would go one layer before, then the weights, then the next layer, then the weights again, then the next layer, then the weights again. Okay. That's how we would compute the gradients. Okay. So now for math, how does the loss change when y changes? What would it be if you had to write it in terms of derivatives? Yeah. So it'd be the partial derivative of L with respect to y1 and the partial derivative of L with respect to y2. Okay. Now these are all functions. Yeah. We'll talk about that. Well, I'll answer your question later. I'll answer your question. All right. So now we go on to the next layer, right? We can represent the previous layer as this graph, okay, and as these equations, and the weight we're interested in is this weight specifically. Okay. So again, like last week, we can split it up into two different single perceptrons, and the equations of which I've written here. So now my question is, how does y change when the weight of 311 change? Or how would you write that in terms of derivatives? Again, this is all just like, I kind of want to drill this in. Everything, So how does, in terms of derivatives, how would you write this? Or I guess, how would you write?
H1 times the derivative of f of 0.
Yeah. So again, only at y1 depends on this weight here. So we would take the derivative of y1 with respect to z1, and then we would take the derivative of z1 with respect to the weight here. Okay. And since we want to figure out the loss, we can then, look at it and then we can multiply it together. Anyway, I have a slight issue with my slide, but you would multiply this together to get your loss of L with respect to the weight. Okay. I think this isn't the right way to think about it, but as a very functional way of thinking about it, I would say you can think about fractions. And then you can just cancel out. That's not the math way, but that's like if you want to think about it this way, it's not terrible here. Okay. Now we want to figure out, what's the loss with respect to our second weight. Okay. So what is H2 of 1 in terms of omega 2 of 11? I mean, weight 2 of 11, or weight at the second hidden layer. Yeah, okay. What are these functions? What are these equations? Maybe you have to write it out. H2 of 1. Sorry, that's a slight notation error. Just what are these two equations equal to? Please. Yeah.
So W11 times the H1.
Yeah.
W21 times H2. Plus W31 times H3 plus
some bias. Okay. Again, some slight notational error. It's supposed to be that. I flipped the indices. Main point is weighted sum activation function. Main point. Okay. And then from here, what is how would you quantify the change in H1 as a function? How would you write that out? As we change, how does H2 of 1 change as the weight 211 change? Yeah.
the partial derivative to
Yeah. Yeah.
then the derivative
Yeah.
with
The weights. Okay. Okay. So again, you can kind of cancel it out to get the derivative of H2 with respect to this weight. Okay. Now, obviously, this weight affects multiple paths here. So in this instance, what would since it affects multiple paths, how would you write out these derivatives? How would we write out these derivatives? These are two derivatives we're interested in. Affects both of them. We want to combine them. Okay. Is this for us? Anyway, yeah.
the partial derivative y1 with respect to h1.
Yeah.
And then you multiply with
Correct. Again, H1 is the only thing that changes as our weight changes, okay? Not these weights. And since Y1 is a function of H1, it'd be like this, okay? Be like this. Okay. And then we want to connect it all together, so we would multiply it all together. And we get this function, okay? Again, it's all you're doing is you're summing over the paths, the possible paths to affect L. There's two paths that can affect L. It's Y1 and Y2. Yeah.
summing
Together to get the, yeah. Okay, does it make sense? Loss can travel this way, W211. Loss can travel this way, W211. So there's two paths again. Okay, it's all about paths, all about paths. Okay. And I guess the algorithm part is if we look at this, what do we notice? What do we see? What do we see? What do we see? Let's say we naively want to update each weight individually. What do we see? What do we see? What do we see? All right, someone else. Someone else. What do we see? Someone new. Come on. Someone new. This is not okay. Someone new. What do we see? What do we see? What do we see? Okay, fine. Yeah.
I think if you update the weight at once,
Yeah.
it will affect the other ones, the other weights.
Yes. Yes, but that's not what I want to show. Okay, what I want to show is if there's a lot of overlapping terms here. If you're updating this specific weight, you're going to have to calculate this. If you're updating this specific weight, you're also going to have to calculate this. So why are we calculating it separately? Might as well, cache it more or less, or store those derivatives, okay? That's the back propagation algorithm. Instead of calculating it individually, you store your calculation in case you want to use it further. It's inefficient. Okay. All right. That's all for me. Yeah.
That's good. Yeah, so well, for the next session, there's not going to be as much math, which is hopefully good for you. So we'll be talking about some tips for just training neural networks in general, and then something you should watch out for when you're doing training yourself. So the first part is initialization. So initialization happens basically whenever you create a new model, you have to start with some weight values, right? And it's probably very bad, as the graph Oscar showed before. It could be something like just a random guess, right? But you have to start with somewhere. Yeah, so does anyone knows some or have any ideas on how should we set those values just in general? Like basically when you initialize a new model, you have to have some weights and then, right? So how do you set those numbers too? Yeah. Hmm? Oh, random initialization? Yeah, that's one way of doing. Oh, yeah.
I guess like
Equally?
yeah.
Yeah, so set them all to the same value, like 0 or something, right? Yeah, so yeah, so zero initialization is probably the simplest way, right? So let's say we have like all the weights and biases, we just set all of them to 0, and then we can start training from there, right? But unfortunately, it doesn't work. I'll tell you that. And so does anyone knows why it doesn't work if we just set everything to 0? Let me see. Oh. Yeah, I don't want to reveal the answer, but yeah. Yeah, okay.
Kind of contradicts like everything we're trying to do. We like try to find the dependency on the weights, and then we say that like every criteria is not important.
Yeah, that's one way of thinking. Anyone else? No? Okay, I'll just review the answer. So recall the equation that, right, when you calculate your shouldn't be y, probably should be z when you for our just proper notation wise. But when you basically how you calculate your activation is y equals to wx plus b, right? So if we set all your weights and biases to 0, so you'll have something like y equals 0x plus 0, which equals 0, right? So as you can see on the diagram, all of your activation would just be 0 in this case, unless you use some like some special activation function like sigma, you get a value of 0.5, but nonetheless, all your activation value will be the same. Yeah, so apparently this is an issue, and does anyone know why it's bad to have like all the activation values to be the same? Like, so now you have all your activation to be 0, but it can be like random constant. Let's say all my activation is 1. Like, why is that an issue?
Like it's a lottery in a sense that it can be like if we use some algorithm, we can like end up with a very, very small time for it to run, or like with a very, very large. But like we want somewhat consistency in the implication.
Wait, so wait, what do you mean like by consistent?
Like we at the end like want our weights to converge to some values,
Mhm,
and if we pick them initially at random, we can like either overshoot a lot
mhm.
or like get lucky. And if we overshoot, that's a problem.
For this case, this is not the reason. It's one of the like reason for other problems, but yeah. Do you have more ideas on why it's bad to have the same values for, yeah,
So that's a big loss.
with the loss?
Yeah, when you calculate the loss, why all the variation is really the same. This particular point. Losses.
Not particularly, because you still have like a loss value, and then you can still calculate the difference between your output and loss. So it's getting closer to, yeah.
Change all your weights to the same number with the same number, so you will always have the constant, the same constant number.
Yeah.
Weights.
Yeah, exactly. So basically, from a loss perspective, right? If you see the last layer, which is the green neuron, to the green neuron, when you're doing backward propagation, which is you calculate the loss and then all the gradients, right? So you start from the green neuron and then you propagate backward. But to the green neuron, since all the activations from the previous layers are the same, every neuron to that final green neuron looks the same as well. So basically what it means is that for every single layer, all your neuron would be learning the same thing. Like, so let's say I trained this thing for like 100 epochs, and then when you just look at the weights, you'll realize for every single layer, all your weights are essentially the same. So basically, there's nothing like each layer you just learns only one thing, but you have a bunch of neuron. Does that make sense? So basically, your gradient for each layer would be exactly the same. So there's no way, like, or there's no point of you having so many neurons, because you can just condense it into one neuron, basically. Yeah, so it says like the neuron becomes indistinguishable, so which means they're all the same. Yeah. So a better idea that we mentioned before would be, oh, if you have all your weights to be the same values, like let's say all zeros or all ones are a big problem, then why don't we just pick a random value? Let's say, right, we sampled a random value from a mean of 0 and variance of 1. Right, so as you can see, weights could have a value of 0.21 or 0.44, or in this case, it can also be negative, but yeah. So yeah, this seems a better way, which indeed it is, but anyone sees any issues with this one?
By keeping like an upper of ones, but I think with that rate, the rules and stuff.
Oh, it's not the one is not the upper bound, it's the variance. So you basically samples a value from like a normal distribution with mean of 0 and variance of 1. So there's no really upper bound, but hopefully you get what I mean. As a hint, it has something to do with the number of neurons. Okay, so no ideas? Oh, yeah. It's okay, yeah. Can take a. Not exactly, because your weights are still in the range, so it's kind of controllable. And then whenever you start with a random weight, it's like always pretty much bad prediction, so you have to update your weights. That's the point of training. So yeah, not exactly as uncontrollable, although it is uncontrollable in this case, but like it's not the reason being the weight value itself. Okay, then I guess we'll just proceed. So remember, well, first of all, the problem it causes is caused whether exploding or vanishing gradient or activation first. So recall for each layer, right? For each neuron, your computation for the value z is w times x, which is basically you sums all over your with n neuron, you sums over n terms from the previous layer, right? And there should be a bias term too. I forgot, but in this case, it doesn't matter too much. Let's just say it's 0, right? So with 2 neurons from the previous layer, then you have your activation would be something like W1x1 plus W2x2 plus a bias term, right? So imagine your like values would be W value would be like 0.2 or 0.5 or something like this. Your sum Z seems to be a all right value. It'd be like 1 or 2 or something, right? So which is okay when you have 2 neurons. But what if you have like 100 neurons in the previous layer, right? Then your activation computation becomes W1x1 plus W2x2 plus all the way to W100 plus x100. So, and then plus B, but you see your summation quickly becomes large, and then with more and more number of neurons, your Z value also grows significantly, which is what we refer to as kind of uncontrollable. Because if I have like 1 million neurons in the layer for some reason, then I'll be summing over 100. No, 1 million. Yeah, 1 million sums, so which is bad. And then your Z becomes a lot larger, and then, right, this is only for 1 layer. So if you have like 100 layers, each with 1 million neurons, your activation quickly blows up. And, right, so, yeah, any questions so far? No? Hopefully this is clear. Okay. And like you might ask, it's just a Z value, right? What if I just limit it with a good activation function? Let's say I use the sigmoid function, which the output is the sigmoid of Z, no matter how big Z is, right? Your value is always between 0 and 1, so it seems your activation is still controllable, right? But unfortunately, forward propagation is not the biggest problem, and the biggest problem comes with backward propagation, which is how you update your gradient. So, yeah, because your gradient depends on the previous layer's activation. So you can write it as some form a of I minus 1, and then I just is the index of the previous layer. But it is a kind of, you can imagine as it depends on the previous layer's activation times a error term. We haven't formally introduced this, but this is one form of writing your gradient, and it's more like it's just a result from the chain rules you'll see before, but there's just more intermediate step before between what you guys saw and then between the results of this. But in this case, if I have like activation of 1 million, then right, that would be very bad. Your gradient becomes very, very large, and then so also your gradient blows up, and then it's just unstable. So, yeah. So how do we solve this problem of blowing up gradients, right? So the fundamental issue actually comes from that our weights grows unboundedly, or not weights, but our summation term, where our activation grows unboundedly with more and more neurons. So basically, we just need to figure out a way that reduce or kind of like bound the summation term instead of just on the weight itself, right? So there's a method called Xavier initialization. And what it does is basically instead of before, remember we use a variance of 1, which is fixed, and then it doesn't depend on how many neurons you have. No matter like you have 1 neurons and then 1 million neurons to it, your variance is still always the 1. So you pick a weights out of that. But in this case, we make our variance dynamic. So this is just a formula they came up with, but it's 2 divided by n number of input neurons plus the number of output neurons. Yeah.
You use this stochastic region this time. You will have the same number of neurons or inputs, or you will have only 1 input at each time?
It doesn't matter because stochastic gradient descent is how many training example you're using at the same time. So it's a batch. So like to each training example, let's say you just have 1 sample, then your computation is the same. But basically what stochastic gradient does is that it processes like multiple training example at once using parallelism from GPU. And you just take the average out of it. So like to each training example, your computation is the same, so it doesn't matter. Does that make sense?
Don't most activation functions like limit the number that goes into the final output so that you never have too many weights? Like if you had like attached as your activation, if you had like really big Z, that was still switching.
Yeah, but like when you compute the activation, your Z value will also get blown up.
Yeah, but it,
Because
like that wasn't like up to between like -1 and 1, so it's okay. Fair enough.
yeah, like for the forward pass, your activation value could be okay, but we are doing computing the gradient. Remember, like you have some terms that involves Z, and then your Z is a very large value. So in this case, there's like, if it makes sense. So like as long as it involves some terms of Z, which is unavoidable, then your gradient has the potential of blowing up. Yeah, where were we? Here. Yeah, so basically, what this formula does is that, let's say, oh, you have more numbers of neurons, then let's make the variance smaller. So instead of making it, let's say I have 1 neuron, the variance is 1. Then if I have 10 neurons, let's make the variance of 0.1. So in this case, it makes the gradient a lot controllable, which is, yeah, like it basically limits your activation and your Z value in a kind of control range, like not strict boundary, but pretty much control range. So that's how it solves the problem. And beyond that, so why is initialization important? So let's say, imagine I have a neural network that something looks like this under the hood, right? So initialization basically means you pick, say, X value to start with. You can either start with from, let's say, very far left or in the middle or very far right. That's how depends on how you initialize your weights, right? And you see the curve has two minimum. One is global and then one's local. So you probably see why initialize is important because it determines which minima you could get, right? If I start somewhere like here, then for my gradient descent, if it's proper, like doing what it should be doing, then it will just go down, 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 and then all the way reach to the global minimum, right? But if I start somewhere like here, then your gradient descent would only take you to a local minimum, which is a suboptimal solution. And for pretty much everything, like all the complex neural networks nowadays you see, initialization is a big problem because it directly determines how good of a solution you could get. And unfortunately, there's no guarantees for complex functions that you would guarantees to find your global minimum. And it's a active research area that's going on just to how to find good ways to initialize a neural network. So if that's something interests you, you can take a look into that, but yeah. And also, we talk about batches. So batches is basically you take a large chunk of data and then you divide it into smaller parts or components. So, well, I asked ChatGPT to generate this image. It's very stupid, but hopefully you get an idea. So you have a bunch of data, and then for each batch, you have a small chunk of data. Yeah, hopefully it makes sense. Does anyone know why we have to use batches though? Like just instead of using the entire training data, like as one, why we need to break it down into smaller parts?
It's too large and wanna have the part of the data for verifying results.
I think it's partially correct if I'm understanding what you're saying correctly. Yeah. Okay. So it's mainly because of memory issue, which is more of a hardware perspective. So yeah, but as you're training, right, you need to load your training data onto your memory, which is your RAM, or your GPU, which also has a RAM, which is fixed size, right? But sometimes your training data is a lot larger than what your memory could fit. So as an example, you have 100 gigabytes of training data, but your GPU only has 4 gigabytes of RAM. then that means you can only upload 4 gigabytes of data to it, right? And then there's no way you can fit all your training data onto there at once. So that's why you need to break it down into batches just to fit your computation limits, basically. Yeah. And some common batch sizes are, you'll usually see if you're trained enough neural network, they're either 32, 64, or 128, or something like to the power 2 to the power of 2. No, the power of 2s. But why we're picking this, well, computers are binary, so it mainly comes from a computer perspective because 2 to the power of 2s, no, what I'm saying. The power of 2s are easy for memory alignment and underlying computations, but there's no really strict rules of how you choose your batch sizes. Like you can use 10, 5, 100, whatever you want. But in general, just the power of 2s becomes a convention. So that's what everyone started using. Yeah, and is this your?
Oh yeah, this is some references for my slides. I would highly recommend if you're really interested in learning more about like optimization or like get like more technical, I would use the Arena Chapter 0. Highly recommend that resource. But yeah.
Okay, let's do part.
All right, we can wait one break for like
sure, we still have time.
Sure.
We can have like
3-minute break.
let's do 2:20. We have 40 minutes, should be enough.
Oh, okay. All right, come back at 2:20. Before you leave, remember to load or run your
Yeah.
run your cells. So
Right.
we'll do that first, then we can break.
Oh, wait, which one? Is this one?
IBM one.
This is-
Oh.
Okay. Which is
Sure.
yeah, if you have any questions for the previous parts, you can also come and ask. Have the solution. I absolutely don't know how to code. Shit.
All right. Remember to
Yeah.
run the first.
You run it already, right? Or can just
Try to run it.
Okay. Yeah, so if you're logging onto the platform before it goes to your break, just please run the first 2 cells because it takes a while to run. So just make sure you can follow along afterward.
I don't know if it's for us. One big. I was not told that pizza would become terrible. It's actually food, it's actually food.
Ask. It's just
No, they just like came here and then they just did it.
I break until 2:20.
Yeah, 2:20, so 5 minutes.
Me and like if like 2 of us speaking, that's surely. Wait,
Really? Yeah, wait.
That's certainly not good for us.
It's great. What the heck? What is this?
I guess you can just type IBM again.
Yeah, that's true.
Literally, let me ask that. Why did it start? Midway through the.
Today.
Okay, then it's.
I just DM'd stuff.
Alright, you guys want?
Wait, can we actually?
Wait, it might get cold, right? I think the play is to, have you guys just started the notebook?
Yeah.
Yes, then it's probably a good time to have some sort of break in between. I think what happened was there was another event happening somewhere around campus. And they must have had a bit of leftovers, so.
Yeah, I got to get fired, bro.
What did Steph? What did Steph?
He literally just came in here, so Steph, the chief of staff to me. He just put all this stuff.
Okay. Yeah, I think what we'll do is we'll do like, a little break. If you guys all like lines up, I don't know how many slices there are, but I think we can go like. It's like a slice and then. Wait. Yeah, I hear.
Okay.
Wait, everyone from the top. Let me.
Right.
But who are you working with? Like a what?
Yeah, I don't. That's probably.
Okay, yeah.
I'll get
Are you on your?
Anyone know if try microwaves somewhere? Are there microwaves somewhere else?
I don't know.
I don't think we have time for it.
This is.
But.
I guess you guys end up.
Oh, that was actually. Yeah, I think that's cheese, those, like, I guess pepperoni, I think there seems to be vegetarian one right below.
The math, not mathing.
Yeah, like keep up with most of your examples.
Which year? Oh, okay, what? Okay.
Yeah, maybe. I could let you guys just like.
Yeah, I mean, I think.
Do you
Can you
have
guys
that, like whether that is relevant?
Is it true?
Research topic.
Okay.
Do you have like a kind of focus that we're like.
Oscar, how much time do you
Yeah, we have like 5 minutes. Let's just do 5
That's
minutes.
enough. Yeah.
Like 2:25. What's your?
like, if we got people to.
So for initial, we need to learn more about the
No, I don't think.
computer.
We should, I don't think we should.
Which is.
It's not
Traditional machine learning.
I think we'll just.
And then.
Yeah, there might be a bunch of them.
Yeah.
I'm gonna check.
Something like that. I think they're typically dealing with. So I suggest you to take some look at those as, yeah, and then if you're getting more application based, I think it doesn't. The math is.
Okay, what are my projects?
Should have like.
No, I wouldn't want to.
You don't want.
If you're-
Oh, yeah, I still want.
So you know.
Yeah, like, it's like.
You've already.
It's like that. Yeah, you never know.
Like you have to.
You're not doing
Forward. I don't even know about those.
That's how I can. Yeah, I can. Yeah, you can start. You can.
You don't know what SIMO is, you don't say SIMO, what does SIMO do?
Getting some airflow.
I love how it's like stealing your pizza and then like later.
Yeah, we're shooting. Second semester will be. Whatever. It's just ideas. First, more just like Jason. So everybody.
You don't even know who Jason like.
No, I didn't.
I'll see like that for the first one.
And you went to. No, you were just.
Oh.
It was like comes through that. So I was like, it's not fair.
Sure, but priority go to. Okay, thanks for your meeting. So it's like, I guess that's take some of the. Because it would be unfair to give everyone, like some.
Yeah.
Yeah. Sure. I mean, I feel like.
Very, very interesting. You don't have to wait.
Yeah, they.
That's not.
Yeah. You wanna go play? So you know what, we have some.
Take one. I want one, that's good.
No, I'm not.
You're not.
At lunch.
Yeah, surprisingly. Seems.
You just wanted to give us about.
Yeah, that project's good.
How's your problem? No, it's good.
No, you can be honest. But I did that.
Cross plots, yeah, we recently. What's that? Where like you extract a vector and then. After extracting a vector, you want to see it causally, like actually encodes it, so you get rid of that. That's the embedding space, and then with the model change here. Yeah. I never understood. Yeah, that's good. It's like. No, that's just like. We. Hard. It's just too hard. Miss. I get it. Me slapper. What? Me slapper. So miss. Miss. No. You know, our slogan should be fully airball. Yeah, yeah.
You can always come up with things, it's like, even if something kills or pregnancy, singing.
Oh. I feel like training dynamics.
Sorry?
Probably got a lot.
Training dynamics?
Yeah, you're gonna put like multiple weight makeup. I'm not cool with that.
Okay, should I start?
You should, you know.
Okay.
Most people seem like good.
What?
Most people seem like good.
Oh, okay. Yeah, so we'll get back on the notebook and yeah, if you guys can be quiet and then hopefully finish eating at some point. So yeah. So I guess for first part of the notebook, which is just to do a quick recap on PyTorch's autograph function. So basically, when you cease your previous computation, backward computations, right, for the slices, you saw you have to do stuff for manually. And luckily, PyTorch has this autograph functions that does everything for you. So if you see this, which we have a simple functions of x equals y equals 3x plus 2 to the power of 2 divided by 2. And so, I mean, it's a really easy gradient to compute manually anyways, but to let PyTorch compute that for you, you can just do y dot backward and then you can print it. Okay, this is good. Just import again. Okay. Yeah, so you can see your derivative for dy dx at that point, which is x equals to 2, is 24. You can verify whether that's true or not, but I think that's true. Yeah, so for now, let's just create a small data set on making a moon data set. So you can just run the cell and then we have 1,200 samples, and then they're a little bit noisy, but we just use the scikit-learn packages to create this data set, and then let's visualize this. So, this is what your data looks like for this case, right? So you just have like two categories of things. So it's kind of similar to what you see in logistic regression. It's a little bit different, but the key idea is the same. And then our goal is to have some network that trains to classifies whether it's a purple point or a yellow point in this case. Yeah. So for now, the next step is we define a model. Should make it bigger. Yeah. So for the model, let's do a 3-layer neural network, which in this case you can run the cell. So hopefully it's pretty pretty simple. So you have 3 linear layers, and then you have 2 ReLU as your activation functions. So if you recall, ReLU as activation functions, it has value of 0 if your x value is less than 0, and then it has just y equals x when your x value is greater than 0, right? So, and the dimension for the first linear layer, you have 2 input feature, because for your data set, all your features is just your x value and then y value. So basically the location of or the position of your points on the graph, right? And for the hidden dimension, we use 32. So we're making sure everything is consistent, right? So 32, 32, 32, and then in the end, we have 2 out features for the probability of x and y, basically. Okay, so here are the implementations that we need to do. For the first one is accuracy, and then the second one is train model functions. So I guess we can have like maybe 5 minutes just for you to do it on your own, and then we'll come back and do it together. my God. Um, you have a solution. Yeah, like on your locally, because I shouldn't just type it out. Maybe I'll just copy it
Yeah,
and then explain it. It's like faster than the
Yeah,
types. Let's just disconnect.
yeah. Oh, I think this should be it.
Yeah. Let's copy. It's just this. It's like, why the hell am I typing for so long? Okay, I'll just start.
I'm
Hmm.
not sure if this is the updated one or not updated.
It's okay, it's just the cells now. I didn't do anything with the cell. Yeah, we're just trying to see if this works. What's going on? Okay. Okay, yeah, so let's just come back. I didn't implement this because it takes a while, so I just copied a solution, but we'll like walk through this together for the implementation. So first of all, you have a accuracy function, right? So basically all it does is compute the accuracy of how well, everyone knows what accuracy is, so I won't explain. But the first thing you do is model.eval basically tells the model to put as a put it into evaluation mode. So it tells, oh, we're not doing training. And so for correct and total, there are just two variables that tracks the number of correct predictions and then the total predictions you make in order to calculate the accuracy, right? So with torch.noGraph, it means that it tells Torch to, because as we said before, Torch will automatically tracks gradients, which is the gradient for you. So in this case, it tells, oh, for accuracy computation or prediction, we don't really need the gradient. So you can like don't track it and then don't waste any like non-needed resources, basically. And so well, let's go back to the data set for a second. So as you see, when we generate it, we generate it in batches, and the batch size is 64. So it means we have total of 1,200 examples, and then we convert it into each batch has 64 data points. So we can convert it into multiple batches. And yeah, basically. And so here, for XB and YB in loaders. So XB is just your training data, which is a pair of XY coordinate, right? So let's say 1.0 and the 0.5 or something. So it makes a pair of your, yeah.
What is load?
Loader is just how you load your data into batches. So here, you see you first can, yeah, so you first get your training data for, right, X train and Y train, which is your X train is your data point, and then Y is your ground truth value, basically your label. And then you turns it into a data loader. So that's how you convert it into batches. And then we also do shuffle. It's just for training. We want a data to have a random order instead of just to make sure it's random order. So yeah. Like the idea is that you don't want to like entire batch of just like all zero prediction, like all zero labels. So that's ideal.
And the batch size is 64 because it's a power of 2.
Yeah, in this case, there's not really like a reason for choosing it. But yeah. It's just like common if you like see lots of different codes, that's probably like 32, 64, 128. Those are the common batch sizes. So yeah, it's more like a convention than like a reason right now. Yeah, so for loader, you load your X and then Y, which is your training data and your ground truth for each batch. And then what you do is you put them onto devices because you need to distinguish whether your device is CPU or GPU. In this case, we only have CPU, so this doesn't really matter. But you just have to make sure your data is on the device when you're doing on the same device when you're doing all your trainings. But that's when you have a GPU access problem. And so logit, which model X of B, so here it just tells the models to predict whatever we have, right? So yeah, I just pass in the X of B and then it will predict the logits. And then logits has the same size as the number of data point you have. So basically it gives a prediction like for each data point. And for the predictions, you just takes in the argmax, which is the maximum values positions of those two. So let's say I have a value, let's say I say the data point is the probability of purple is 0.7 and the other probability for the point is yellow is 0.3, then we pick the 0.7. And argmax actually picks the indexes, but it's more of a programming issue than what you were concerned. But in this case, it picks the model's prediction on whichever is thinks correct. So, and then what we do is just we ask the total number of correct predictions to your correct values, and then also your total number of prediction you made to the total. And then in the end, you loop through all the batches, which is you've done all your predictions for every single data point. And yeah, in the end, you just returns the accuracy for the number of correct divided by the total. Yeah.
What is new
Number, it's num element. So what it means is just returns you the number of elements in Y. So basically returns the total number or the batch size of that case. Yeah. So in this case, every time you add close to 64, and then in the end, you end up with 1020 because that's your data size. Yeah. Are we good with the accuracy? Yeah.
Line, second last,
This one?
yeah, we need an item because of the previous line, judging by index.
No, it's because the number of corrections. So you have predict equals YB, right? It will gives you a vector of size 64 because that's the number per batch. So you have 64 predictions, which is whether 1 or 0 or something like that, right? And then you do a summation, but it's still a vector. So for item, you just to extract it to an integer or whatever. So it's just like a data type conversion problem. Are we all good with this?
Are going to go over all the batches.
Yeah. So this line is how you loop through every single batches in your data loader. Okay. So for the train model part, we'll have two different types of optimizer that we'll experiment with. So one is stochastic gradient descent, and then the other is Atom, which is a more advanced version of optimizer. And then in this case, we just select by their name. So in this case, you just set up to optimizer with their model's parameter and learning rate for the first 4 lines. And then for the next criterion, which is your loss function, we use cross entropy loss. So hopefully you guys see that in week 2 and week 3 probably as well, right? So hopefully you guys remember what that is, but it's just like a negative log of your predictions, and then it basically tells you how good the model prediction is, right? So here we have the formal training loop. So we just created a 3 arrays to track all of our values for training loss, validation loss, and then validation accuracy, just for tracking purposes. And then here for epochs, so our original epochs were set to 50, so we trained for 50 loops basically. And yeah, so here models.train, we tell the model, oh, that we're training, you should probably make some adjustments to start training. And running is just the thing that we use to track our loss. And similarly, you've seen this line before. So for each epoch, we'll loop through all the data in the batches, right? So you have XB and YB, which is XB is your data point for that batch, which contains 64 elements, and then YB is your ground truth. So which like whether 0 or 1, and it will it will basically tell the models and it will use it to calculate the loss. So again, we set it to device, doesn't matter too much in this case. So optimizer.zeroGraph, this line doesn't, all it does is that it sets the previous gradient computation all the way to 0. So in case your gradient accumulates. So it's kind of like you have a variable that you used previously, and then when you want to refresh it, you have to set it back to 0. So that's all it does. Nothing fancy. So logits you've seen before, right? Just make a prediction from the model, and then loss. We use the cross entropy loss, and then we pass in the logits, which are the model's predictions, and then YB is your ground truth. So we can use to calculate the total loss out of it. And loss dot backward, as we seen multiple times, it tells PyTorch, oh, compute this gradient, compute all the gradient for me for this loss function, right? And optimizer.step, it just tells you optimizer to, oh, add this model parameters, help me update it. And then running plus loss.item is just, oh, like, let's keep track of the loss we have. So yeah, any questions for the first part? And then the last line is just also for tracking purposes, your append your loss.
What is running? Running
Oh, running is just keep track of the loss per batch. But your total loss is the summation of all the batches. So that's just like a temporary variable that you need to keep track of. Yeah. Okay. No more questions? Okay. So, and then for models.eval, what it does is just that it will evaluate after each training epoch how well your model performs on the test set. So model.eval tells you, oh, let's do evaluation again. No needs to track of gradient here, right? And then we do vloss, and then YB, XB, YB, and then in this case, we're using the validation set. So which is the model, right? What the model haven't seen before. So it's the test set basically. And then we'll just see how well it does. So we make a prediction, and then we calculate the loss, and then we see how accurate it is. Yeah, so any questions for this? Let me just add quickly add a print line so we can see some results afterward. But Mhm. Okay. Okay, yeah, so I just, all of those just add a print line, so hopefully it'll give some print results when we train some model. So if it runs the next cell, it will start training, and then as you could see, you have your training loss is going down, and then your validation loss is also kind of going down. And then in the end, we just plot a curve of your training data and your validation data for this case. And yeah, interestingly, your validation loss is a lot lower than training for some reason, which is interesting, but yeah, probably didn't normalize this, but whatever. Yeah, so any questions so far? Okay, okay. So while we have the model, why don't we just plot the decision boundary, right? So you can run the next cell, and then it gives you a pretty nice decision boundary. So it tells, right, purple, it means it has 0 probability of being the yellow point. And then the yellow part just tells you that it has a higher probability of being classified as a yellow point. So yeah, and then you'll see for the top left, yeah, top left, it's all pretty much all purple, because in that range, the model is being very confident that, oh, this point is probably purple, right? And then similarly for the bottom right, it says, oh, it's very confident that this thing is the point is a yellow point. And then in the middle, you'll see some like changes or variations in the decision boundary. So it has different probability of classifying things, because those are where the 2 data points could mix together. Yeah. And the last step is just that we do some small experiments on how each sorry, let me just uncomment on this when I run this. The last step is just we do some small experiments on different optimizers. So in this case, we have 2 optimizers and 2 settings. So we have stochastic gradient descent with a learning rate of 0.01 and then 0.05. So one is smaller, one is larger. And then also we have Adam optimizer, which has a learning rate of 0.01 and 0.001. So yeah, we'll just see how the performance of these 4 optimizer looks like, and then also take a look at what happens if you have different learning rates. Yeah. So this is the graph. As you can see, Adams does a lot better than stochastic gradient descent for the earlier epochs. It has a quicker convergence because it's a more advanced, more optimized algorithms. And yeah, so for the red curve, it's an Adam algorithm with a learning rate of 0.01. But it seemed to me like it's kind of like jumping around a little bit, right? So does anyone know why is that the case?
The number of epochs is the number of, how do you calculate the number of
Epoch?
people?
Epochs are what you said. So number of training loops you said.
How do you set this number?
It just depends on how long you want to train your model.
Okay, does it have a link with the batch size and the size of the?
No, that's a hyper, yeah, they're both hyperparameters you determine yourself. It's not really related. So epoch is just like how many times you train your model, basically. So higher the epochs, the more you train your model.
In one epoch, you go over all the data set.
Yeah, for one epoch, you do 1 iterations of your entire data set and then make updates to your weights. So over 1 epoch, you make 1 updates to all your weights.
But You go over all the data sets or just one batch?
The entire set.
Okay.
But in order to go over the entire data set, you need to do by batches. So that's 2 steps.
After each batch, you do back propagation.
No, we like kind of keep track of the computation. And then after we go through like all the batches, which is the entire data set for one epoch, we do one back propagation. Wait, is that true?
I think I think that's true for batch, but I think for SGD you.
Oh yeah, sorry. Yeah, for SGD you make a gradient, like you make a gradient update after each batch.
And for Adam, it's after you went over all the batches.
No, Adam has a different ways of computing the gradients.
Yeah.
Not really different, but like more optimized way of computing gradients. That's more advanced algorithm, which is not what we're concerned about in this case. But you can just know the term because it's very commonly used. Optimized. Yeah. Yeah, so back to the original question, does anyone know why is the edge curve kind of jumps around? Yeah.
Because its depth is like 0.01, so it's like bigger and it passes over the global.
Yeah, exactly. So because in this case, your learning rate is a lot bigger, right? So your stuff kind of jumps around, and basically kind of already reaches the local minimum, whatever you have, but it's just kind of jumping around between 2 points. So that's why you see the zigzag pattern. And if we actually change it to something small, which is what I experimented, so you can do 0.015, then you'll probably see a smoother curve, hopefully. Yeah, it takes a bit to run, but yeah, that's pretty much it for today, though. This after this runs. Yeah, so you see the red curves becomes a lot smoother. So that's when you have a smaller learning rate, then it means your things going smoothly downward towards your local minimum. Yeah, so suppose that should be it then, if we don't have more questions.